What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 6, Section 7, Exponential and Logarithmic Models. Let's do it. So for this first question, it says, with what kind of exponential model would half-life be associated? And this would basically be something where it's an exponential decay, because half-life, it's like something's getting smaller every certain period of time. So for example, if you have a half-life of 5 years of some compound, that means every 5 years, half of it is going away. So if you start out with 100 grams, in 5 years, you'll have 50. In 10 years, you'll have 25, right? Half of this. In another 5 years from this, you'd have 12.5. So that's sort of your half-life. It would be exponential decay. And again, half-life is that period of time that it takes for half of the amount of this substance to go away, to disappear. So that's how you do it. Done. With what kind of exponential model would doubling time be associated? With what roles does doubling time play in these models? So we're talking about exponential growth, okay? And in this case, what we're talking about is we'd be saying like y equals, let's say 100, that'd be our initial value, times 2 to some exponential power. This is doubling, okay? And in this case, right, you'd plug in 1, it would double to 200. Plug in 2, it would be 2 squared, which is 4 times 100, which is 400. So again, in this case, it's doubling every time x increments by 1. And once again, doubling time is the amount of time it takes to double. So in this example, it would be every 1, let's say, hour or 1 minute or whatever. If I had this as x over 5, now it'd be different. Now it would take 5 hours or 5 minutes, depending on the unit, for this to double. So that's what doubling time is. Boom, done. What is an order of magnitude? So an order of magnitude is when we're trying to describe something by the nearest power of 10 in terms of growth. So for example, if something grows by 10, right, we'd say that's 1 order of magnitude. So we're going, let's say, from 5 to 50 to 500, etc. This would be 1 order of magnitude growth, right? 1 power of 10. What if instead it was going by 7 to 700 to 70,000? Now we're growing by 2 orders of magnitude, aka 10 to the second power, or 100. One example that they give in the back of the book is Saturn, for example, is 100 times or 95 times, let's say, as larger than Earth, right? So if we're looking at that as an order of magnitude, well, 95 is really close to 100. 100 is 10 to the second power, so we'd say 2 orders of magnitude greater than Earth. So that's an example of how you'd use it. Done. So for this one, it says find and interpret f of 0 for this logistical model. So what it means is we're just basically plugging 0 in for x here. So we have 150 over 1 plus 8. E to the negative 2 times 0 is just 0. E to the 0th power, or anything to the 0th power, is 1. So it just becomes 150 divided by 9. And then this 150 over 9, top and bottom can be divided by 3. And then we got 50 over 3. So we're going to plug this into Desmos and get the decimal approximation. So 50 over 3 would be 16.666 repeating, which would round to approximately 16.7. So if we are basically going to interpret this, when they're saying f of 0 in a logistic model, assuming that 0 represents time, this is the quantity roughly at time 0, boom, done. So for this one, it's asking to find the carrying capacity of this logistic model. And the nice thing about that is we can find it by just looking at the numerator. So the carrying capacity is simply 150, boom, done. So this one, we're meant to determine whether this is linear, exponential, or logarithmic. Now, I can immediately tell this is not linear because it's not going up by a constant amount. Like here, it's going up by 0.2, then it's going up by 0.24. So it's definitely not linear. And it looks like it's growing, which leads me to believe that this is an exponential growth model. And we can kind of figure that out because if you look at it here's the really telltale thing. It looks like it's basically multiplying by 1.2 every time. So it's powers of 1.2 like so. And if it's powers of 1.2, it should literally be 1.2 to some exponential power. And you can see you plug in 0, you'll of course get 1, or anything to the 0th power is 1. Plug in 1, you get 1.2. Plug in 2, you get 1.2 squared, which is like 12 squared, which is 1.44. 12 squared is 144. So you can see right off the bat, this would be the model, boom, done. So for this one, we're going to plot this in Desmos, and we're going to see if it represents logarithmic, exponential, linear, etc. So here we have all the points plotted out, and you can see that this has a nice logarithmic look to it, right? It's kind of going across and it's leveling out, but it's still going to go up and up and up forever. And here it looks like it's got vertical asymptote at x equals 0. So 13 is definitely logarithmic. Boom, done. For this one, once again, we're going to plot these coordinates out in Desmos, and then we're going to try and see what type of function it is. So as we plot out these points, you can kind of see it going off in this direction. And again, it looks like it's leveling off. So this, again, looks logarithmic. So 15 is logarithmic. Boom, done. So first it says using a graphing calculator, graph this function. So we're going to use Desmos. So when we graph this logistic function, setting it like this, we can see here, it's got that nice y-intercept of 0, 100, and then it kind of maxes out at 1,000. And that's because that's the capacity, right? And that's that constant on the top there. So that's how you do it. Boom, done. So for this one, it's asking what is the doubling time for the fish population. So the way we can kind of figure this out is we can figure out, at time 0, what is the population by plugging in 0 for t, and then figure out how long it's going to take for that to double. So if I plug in 0 for t, I get e to the 0th power, which is 1, times 9, which is 9. So I end up getting 1,000 over 1 plus 9. That's 1,000 over 10, which is 100. So at time 0, we have a population of 100. So then I want to know how long is it going to take to get to 200. So now we're going to plug in 200 for p, and we're going to solve for t. So we're going to start by multiplying both sides times that denominator. So 200 times that denominator is 200, plus 200 times 9 is 1,800, e to the negative 0.6t, and this equals 1,000 because when I multiply the right side by the denominator, it just cancels that denominator out, so we have 1,000. Now I'm going to subtract by 200, and I get 1,800 e to the negative 0.6t equals 1,000 minus 200, which is 800. Then we're going to divide by 1,800, and I get e to the negative 0.6t equals 800 over 1,800, which is 8 over 18, which is 4 over 9. Now, since I have an e and an exponential variable, I need to take a log. I'm going to take natural log because we got e there. So I'm going to take natural log of both sides. That's going to cancel that out and allow me to bring this down to be negative 0.6t equals ln of 4 over 9. Last but not least, I'm going to divide both sides by negative 0.6, and we're going to get our approximation for t. We're going to use Desmos to get that approximation. And rounding that up is going to be 1.4. That's to the nearest tenth. So it takes approximately 1.4 years. Finally, just one other last thing to know when it says what is the doubling time for the fish population. Since this is a logistic function, the doubling rate doesn't stay consistent, right? So for example, in an exponential function, the doubling rate is consistent. Let's say it's 5 days, it's always going to be 5 days. For a logistic function, it kind of speeds up and then the rate of growth slows down. So this is just a doubling time for the fish from that initial population, just to clarify. So for this question, it's asking how long will it take for the population to reach 900? So we're going to plug in 900 for the population, and we're going to solve for t. So I'm going to start by multiplying both sides by this denominator. So 900 times 1 is 900, plus 900 times 9 is 8,100, e to the negative 0.6t equals, and then you multiply the right side by the denominator, and it just cancels out the denominator, so you get 1,000. Next, I'm going to minus by 900 on both sides, right? And that's going to get rid of that, and that's going to be 100. And then we're going to divide by 8,100. So we have e to the negative 0.6t equals 100 over 8,100, which is the same as 1 over 81. Then we need to solve for this exponential variable. So I'm going to take the natural log. We need a logarithm, but I'm choosing natural log because we have an e here. So that's going to be nice because natural log of e is going to just be 1. And then we can bring this exponent down, and we have negative 0.6t equals ln of 1 over 81. Last step, we're going to divide both sides by negative 0.6. So we get t equals ln of 1 over 81 divided by negative 0.6. So we're going to evaluate that in Desmos and get an approximation. So here we get 7.32, rounding to the nearest tenth would be 7.3. So the answer is approximately 7.3 years. Boom, done. A substance has a half-life of 2.045 minutes. If the initial amount of the substance was 132.8, how many half-lives will it pass before the substance decays to 8.3 grams? And what was the total time of decay? So we're going to start by plugging into a exponential equation. So we'll say the amount of the substance equals the original amount, 132.8. And then since this is a half-life, we'll say times 1/2. And then the half-life is 2.045 minutes. So we usually do t over that half-life, which is 2.045. And then we're trying to figure out when this substance is going to have a mass of 8.3. So we're going to plug in 8.3 for A and solve for T because we need that time of decay. So we got 8.3 equals 132.8 to the times 1/2 to the T over 2.045. Now we're going to solve. So first we're going to divide both sides by 132.8. Then I have 1/2 to the T over 2.045 equals this fraction. Now we want to get this down from the exponent. So again, I could take natural log base 1/2. That will just annihilate the 1/2 here, right? So I can just say log base 1/2 of both sides. By the way, I could choose log base 10, log base e, which is natural log. It doesn't matter. I'm just choosing this so log base 1/2 of 1/2 goes to 1, and then we can bring that nice exponent down to simply t over 2.045, which equals log base 1/2 of 8.3 over 132.8. Last step, we're going to multiply both sides by 2.045, so t equals 2.045 times log of 1/2 of 8.3 over 132.8, and now we got to plug it into the calculator and see what we get. And we get 8.18, so that's the amount of minutes. That's the second question, right? Total time of decay is 8.18 minutes. And the question is, how many half-lives is this? Well, this is one half-life, so I just basically divide 8.18 by the 2.045. And once we do that division, we get exactly 4. So this is 4 half-lives, which is a total of 8.18 minutes. There's your answers. Done. Recall the formula for calculating magnitude of an earthquake. Show each step for solving the equation algebraically for S. So basically, we're isolating S. So let's start by first getting rid of the 2/3, which is multiplying by the reciprocal of 3/2. Now we're into this equation, which is log base 10, right? If there's no base, it's base 10. Log base 10 of this equals this. Now we can convert this to its exponential equivalent, meaning it's 10 to this power equals whatever the argument was, which was S over S null. I know that looks like a 5, but it's S. And then we're trying to isolate S, so last step we multiply by that denominator of S null, so we get S equals S null times 10 to the 3 over 2m power. That's the isolated version. Done. So for this one, we're trying to prove that b to the x equals e to the x ln of b. So the way we can prove this is we can start by setting some variable y equal to b to the x, okay? And what we're going to try and do is we're going to try and see if we can get something equivalent here. So I'm going to start with this premise, and then I'm going to start by taking the natural log of both sides. So by doing that, I can use my exponent rules, which allows me to bring this x down as a coefficient. So now I know that ln of y equals x ln of b. And by the way, I'm just going to put up our original premise, which was y equals b to the x. So just so we remember the chain of actions, we started with this, then we took log of both sides, then we brought the exponent down. Then what I'm going to do is I'm going to convert this to its exponentially equivalent form. Remember, this is log base e, natural log base e of y equals this. To convert it, I can say this is the same as e to the x ln of b equal to y. Now, why is it interesting? Because I said y equals e to the x ln of b. I also said y equals b to the x. And if they're both y, it means that these two are indeed equal. So that's how you prove it. Done. So for this one, we're meant to write an exponential model representing the amount of drug remaining in a patient's system after T hours. And it says that it starts with 125 milligrams that decays at 30% per hour. So the way we'd have it would be the amount left in the body starts with that initial value of 125, and then it decays by 30%. That means inside the parentheses, it should be 1 minus 0.3, aka 0.7, and it says by every hour. So I can just put this to the t power or to the x, either way, but that represents the number of hours. Now we can use this to solve for this for 3 hours. So I'm going to plug in 3 for t, and let's see what we get. So plug this into Desmos and let's evaluate it. And here we get 42.875, which would round up to 43. So our answer would be 43 milligrams. Boom, done. For this scenario, it says a tumor is injected with 0.5 grams of iodine, which has a decay rate of 1.15% per day. So it says, how long will it take for half of the iodine to decay? So we can start by setting up an equation saying the amount is equal to my original value, which is 0.5, right? That's how much we start with, 0.5 grams, with a decay rate of 1.15, which means it's minus this as a decimal, 0.0115. And then this is per day, right? Decay rate per day. So then we can just put that to the t power. And then we're saying to the nearest day, how long will it take for half of this to decay? Meaning we should be down to half of 0.5, which is 0.25. So now we have an equation. And now we can solve. We're going to first start by dividing by 0.5. 0.25 divided by 0.5 is 1/2. Now to solve for this exponent variable, we have to take log of both sides. I can take any log I want of any base. I'm just going to do log base 10 because it's easiest to write and easiest to plug into the calculator. So we're going to take log of both sides. That allows me to bring the t down as a coefficient in front here. So now I have log of 1/2 equals t times log of 1 minus 0.0115, and that is 0.9885. So then last step, we divide by log 0.9885. So then we get this expression. Now let's plug it in and see what it approximates to. And we get 59.9, which we're going to round up to 60. So we can say approximately it will take 60 days to decay that amount. Boom, done. So for this question with the 250 grams starting and then at 250 minutes, we know it's decayed to 32 grams. We can create an equation for this, and we're going to do so using the base of E. So we know that it's A equals my initial value, which is 250 grams times E to the kt power. Now, the first thing I need to figure out is what is K. And to do that, I'm going to say that 32 is A. So when I know that A is 32 grams, when it's decayed to 32, I know that my time value is 250 minutes. So now I've got enough to solve for K, and then we can have our equation. So first I'm going to divide both sides by 250. Then to get this variable out of the exponent, I have to take a log. So I'm going to take natural log of both sides. Again, that's arbitrary, but I like taking the natural log of E because that goes to 1. And then when this comes down, we just got K times 250 equals this natural log of 32 over 250. Then last step to solve for K, we're going to divide both sides by 250, and we're going to see what that is. And then we get for K negative 0.00822. So we have A equals 250 E to the negative 0.00822 times T. And now the question is, what is the half-life of the substance? Meaning, how long does it take for half of the substance to go away? Well, we can figure that out now with this equation. We can plug in 125, exactly half of the original amount, and solve for T. So first we're going to divide by 250. 125 divided by 250 is half. Then to bring the exponent down from here, we're going to take the natural log of both sides. So again, that's going to cancel out to 1, and we're going to just have negative 0.00822 t equals ln of 1/2. Last step, we're going to divide both sides by negative 0.00822. This will cancel out, and then we'll get our final answer for the approximate half-life. So let's see in Desmos. And then we get this approximation of 84. So the half-life is approximately 84 minutes. So here's one of your answers. Here's the other one, the equation. Boom, done. This question says the half-life of erbium is 10.4 hours, and we're trying to find the hourly decay rate. So let's see if we can figure this out. So we can say A equals some initial amount E RT. And what we can say is when we plug in 10.4 for T, we should have half the amount left then that we started with. So if I start with 1, then it's just E to the R, and then T, as I mentioned, is 10.4. We know that we're going to end up with half of 1, which is 1/2. So this is a nice starting equation to solve for R. Now, since that's a variable in the exponent, we have to take a log, aka natural log. Since we got a base of E, that's going to make it nice and easy. So we got ln of 1/2 equals, this comes down as a coefficient. Ln of E is just 1. So now we have 10.4 R, and then we divide both sides by 10.4, and we're going to use Desmos to get this. So we get negative 0.0666, which we can round to negative 0.0667. So as an hourly decay rate, right, we can say it's decaying at 6.67%, right, if we move the decimal over twice. So down to an hour, it's a decay rate of 6.7% per hour. There it is. Boom. A research student is working with a culture of bacteria that doubles in size every 20 minutes. The initial population count was 1350. Rounding to 5 decimal places, write an exponential equation representing the situation. And then to the nearest whole number, what is the population size after 3 hours? So we're going to start with A equals initial 1350 E to some RT like so. Now we also know this is going to double in 20 minutes. So I can say when this is doubled, aka 2700, that means time is 20. So now we have an equation where we can solve for r. So let's do that. First, we're going to divide both sides by 1350. 2700 divided by 1350 is 2. Now to bring this exponent down, we're going to take the natural log of both sides. That's going to allow me to bring this down. And natural log of e is just 1. So we got r20, or 20 times r, equals ln of 2, and then we divide both sides by 20 to get r, and I'll see that in Desmos, and we get 0.03466. So there's your equation. That's the first part. Now the second part of the question says, to the nearest whole number, what is the population size after 3 hours? Now, again, remember with t, we're doing that in minutes. So when we're saying 3 hours, we got to plug that in minutes. 3 hours is 3 times 60 is 180 minutes. So we're going to plug and chug here. We're going to do that in Desmos. And so when we plug it in exactly without any rounding, we get 691,200. So the population at 3 hours is approximately 691,200. Boom, done. So for this one, we're starting with the scenario that a biologist recorded a count of 360 bacteria in a culture after 5 minutes and 1,000 after 20 minutes. So using this, we can create kind of two equations, and we can see that the bacteria is 360 with some initial amount of bacteria at 5 minutes. So t is 5. So we got one equation. Then we got a second one where it's 1,000 with that same initial value, which we don't know what that is yet, e to the r times 20 minutes. So now we have a system of equations which we can use to actually solve for r and p. So what I'm going to do for this first one is I'm going to actually divide by e to the r5, or e to the 5r, and get a value for p. And then I'm going to take this and I'm going to plug it in for p up here. So now I have 1,000 equals 360 over e to the r5 times e to the r20. Now what I can do in this case is I can actually subtract these exponents because I have the same base. So 20r minus 5r is 15r. Then we're going to divide both sides by 360 like so. Then I have 1,000 over 360 equals e to the 15r. So now to solve for that exponential variable, we have to take the natural log of both sides. And that's going to turn into 1 and allow me to bring this down as a coefficient. So now I have 15r equals ln of 1,000 over 360. And the last solve for r, we divide by 15 like so. And we get 0.06811. So there we have a value for r. Now to solve for p, we can just plug this value into this equation. So I plugged in the exact amount. I didn't round it. So it's 360 over e to the 5th power times this value, 0.068110, but I left it in as exact, and we get approximately 256. So rounding that to the nearest unit, we'll say the original population was 256, which means now we can have a nice final equation of a equals initial 256 times e to the r, which is 0.068110, times t. And again, this is now all in minutes. Now, if we're trying to figure out how long it takes to double, what we're going to do is we're going to plug in 512 for a and then solve. So the nice thing is when we plug in 512, it equals 256 times this, divide by 256. So I'm going to jump ahead and we're going to start with 2. So 2 equals e to the 0.06810t. Now to solve for t, this exponential variable, we have to take the natural log of both sides. So I know we're running short on room, so we got ln of 2 equals, ln of e just turns into 1, and that brings it down as a coefficient. So now we have 0.06811t. Last step, we divide both sides by 0.0681110, and we're going to do this in Desmos. So it's ln of 2 divided by 0.0681110, but I plugged it in exactly, so we get a nice value here, and we get 10.17, which we can approximate to the nearest unit as roughly 10 minutes for that doubling time. So 10 minutes is how long it takes to double. There's your equation, done. So for this exercise, we're actually going to use Newton's law of cooling, which states that the temperature will equal a e to the RT plus my temperature in the room. We could say T sub S. So since I know the temperature in the room is 69 degrees, we can plug this in here. Now, the first thing is I need to figure out what A is, and I can figure that out with this internal initial temperature of 100. That's going to occur when T is 0. So when T is 0, that's e to the 0th, which is just 1. And then T would be 100. So I'd have a temperature of 100 when T is 0. So that's 1 times A, which is A, plus 69, which means A equals 100 minus 69, which is 31. So now I can rewrite this equation as T equals 31E to the RT plus 69. Now I have one other piece of information that's going to help us solve for R, which is that after 15 minutes, we get a temperature of 95. So temperature of 95 equals 31e to the r times 15 plus 69. Now let's solve for r. So we're going to subtract 69 from both sides, and that's going to give me 26 equals 31e to the 15r, right? R times 15 is the same as 15r. Divide by 31, 26 over 31 equals e to the 15r. Now to solve for that exponential variable, I take the natural log of both sides. That allows me to bring this down as a constant, and ln of e is just 1. So now I have 15r equals ln of 26 over 31. Then I can divide both sides by 15 to get r. So r equals ln of 26 over 31 divided by 15. Let's get the approximation in Desmos. And we get negative 0.011726. So there's my r value. So now I can rewrite this equation as t equals 31e to the negative 0.011726 times t, and then all of this plus 69. And then it says to the nearest minute, how long will it take for the soup to cool to 80? So we're going to plug 80 in for t, and that's big T, by the way. So making a little room here, we got 80 equals all of this, and then now we're going to subtract by 69, so we get 11, and then we're going to divide by 31. We get 11 over 31 equals e to the negative 0.011726t. Okay, so we got a lot of stuff here. Then again, to bring this exponential variable down, I'm going to take the natural log of both sides. So that's going to turn into 1, and then I got negative 0.011726t equals ln of 11 over 31. And then last up, we're going to divide by this negative constant. And to get the approximation, we're going to do that in Desmos. And we get this nice approximation of 88. So the final answer is 88 minutes. There you go. Boom. Done. For this one, we're meant to write a formula that models the situation. And again, we're going to need to use Newton's law of cooling. So the temperature is equal to some constant times e to the RT plus whatever that temperature is in the room that it can cool to. So the lowest it's going to cool to is 75. Now we're also starting at time 0 with the temperature of 165. So when I plug in 0 for t, that's e to the 0th power, which is 1, times a, which is just a. And then a plus 75 equals that temperature of 165, which means if I subtract by 75, a equals 90. So now I have t equals 90 ERT plus 75. And then the last thing I need to do is I need to solve for r. And I can use this right here. It says after a half an hour, the temperature is at 145. And since this is in minutes here, and we're going to do this in minutes. So it says a half an hour, that's going to be when t is 30. So we've got 145 equals 90 e to the r times 30 plus 75. Now we're going to solve for r. So we're going to subtract by 75 from both sides. And we get 70 equals 90 e to the 30r. Then we're going to divide by 90. 70 divided by 90 is 7/9. And that equals e to the 30r power. Now we're going to take natural log of both sides because we're trying to bring that exponent down. This allows me to bring it down as a coefficient, and ln of e is 1. So now I have ln of 7/9 equals 30r. Last step, divide by 30, and we're going to approximate using a calculator. And for r, we get negative 0.008377. So now we have our final equation where the temperature equals 90 e to the r, which was negative 0.008377 times t in minutes, plus that last 75 like we have up here. And here is your equation. Boom, done. So for this question, you have to look back to 43 to know how we got this equation. So if you need to refresh your memory or you're having trouble getting this equation, look at 43. But now we're in this equation saying how long will it take to cool to 110? So this is what we plug in for t and solve for little t. So first I'm going to subtract both sides by 75 and we get 35. Then we're going to divide both sides by 90, and that's 35 over 90. Then to bring this variable down from the exponent, we're going to take log, and I'm choosing natural log because natural log of e turns into 1. So as we bring this down as a coefficient, this just goes away. Now I have ln of 35 over 90 equals negative 0.008377t. Last step, divide by negative 0.008377 on both sides. And now let's plug it into Desmos to get our approximation. So here we get 112.7, which will round up to 113. So we'll take approximately 113 minutes. Boom, done. So for this one, if we're trying to figure out this value, I'm going to first say log of x equals that value, which appears to be 1.5. Then to figure out this value, I'm going to take the base of this logarithm and raise it to that power. That's just converting it to its exponential equivalent. So 10 to the 1.5 equals x. And when you plug it into a calculator, it equals approximately 31.623 if we round up. So we'll say approximately 31.623, boom, done. So there's a little bit of a clever way that we can solve this one when we've got this magnitude equation. So we start with this magnitude of 3.9, and this is equal to 2/3 log of S, which is actually the magnitude of the earthquake, or the energy of the earthquake, I should say. And then S null is some constant. So the first thing I'm going to do is I actually want to isolate this logarithm, and it's just going to make it a little bit easier. I'm going to multiply both sides by the reciprocal of 2/3, which is 3/2. And when we simplify it down, we get 5.85. So now what I'm going to do is I'm going to go back to my original equation, try and figure out the magnitude for something where it's now 750 times greater. So its magnitude equals 2/3 times log of, and to increase the energy by 750, it's literally 750 times whatever we used to have. Now, this is great because I can use my logarithmic rules, because when I know that the arguments are being multiplied, it's the same as breaking it up into addition. So watch this. So now I can separate it as log of 750 plus log of this times 2/3. And the great news is, look, we already know what log of S over S null is. It's 5.85. So now I can plug and chug and solve for M. So now I've got M equals 2/3 times log of 750 plus, and then I'm substituting in 5.85 for this piece, 5.85, and let's plug it into the calculator. And then we get a nice magnitude of 5.816, which rounds to 5.82. So 5.82 is the magnitude to the nearest hundredth. Boom, done. So for this question, we've got this formula, this logistic function representing this model, and it says to the nearest whole number, how many people, and again, remember, n is the number of people, will have heard the rumor after 3 days, and t is the amount of days. So this is a straight plug and chug situation. I'm going to plug 3 in for t in the calculator and evaluate. So just by plugging and chugging, I get 71. So to the nearest whole number is 71. Boom, done. So for this one, it says a doctor injects a patient with 13 milligrams of radioactive dye that it decays exponentially. After 12 minutes, there are 4.75 milligrams of dye remaining, which is an appropriate model for the situation. So for me, right off the bat, we're talking about exponential decay, and a logistic function doesn't make sense. So I'm actually rolling with one of these exponentials. So let's think about a model. We know it's A equals my initial amount, which is 13 milligrams times e to the RT. And we don't know what R is, but we have this nice little additional piece of information where at 12 minutes, we have this many milligrams left. So A is that. So we got 4.75 left when t is 12. So r times 12, and now we can solve for r. So I'm going to divide by 13 first, and then we have 4.75 over 13 equals e to the r 12. Then we're going to take natural log of both sides, because that's going to bring this exponent down, and also ln of e is 1, so that goes away. So now I have r12, or 12r, equals ln of 4.75 over 13. Last but not least, we're going to divide by 12, and we're going to solve for r. So we're going to use the calculator, and we get negative 0.0839. So now as we plug it back into our original equation, we get a equals 13e, and then r is to the negative 0.0839, and then to the t power. And which one does that match? It matches exactly with c. So C is the winner. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more videos from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.